Good afternoon, I think. Okay, yeah, it's afternoon. Thank you so much for joining my talk. So today we'll be seeing how you can leverage blockchain to improve the security in OTA firmware update infrastructure. So let's begin. I'm Swapnil Shinde, yeah, and also I've been part of various open source programs like Google Summer of Code. I've been part of OWASP, where I was working with private blockchains. So OWASP is actually security related. So we were improving security using in blockchains. So cool. Okay, so let's start. So there are two types of updates in how you can update your IoT. So first one is, sorry, okay. Yeah, so first one is your wired, using wired method. So here you connect your IoT device using a physical link, which is your USB in case of this, and in case of Arduino, it's some type of cable. I don't remember that. Okay, so this is the most safest way because you're directly physically connecting to the IoT device. But there's another way. This way is not that practical because obviously in production environment you won't be like connecting to your car and then updating that firmware. The second way is over the air update, which is most widely used here. Like you have a centralized OEM server and then you push the update like the vendor. Hello. Okay, so the vendor pushes that update wirelessly and your IoT device will pull that update from the centralized server. But since it's wireless, so and also a centralized server is being used, it is not that secure. And now we'll see how we can improve the security of this system. Okay. So yeah, so these are the problems with OTA updates. The first one is firmware blues, in which like the attackers try to push malicious code into the IoT device, and the malicious update will be like the IoT device will behave maliciously, obviously. And the second one is DDoS attack, in which the attackers like sniffs in between and then like flushes your device with random packets, and your device will get into the boot loop. Third one is servers under siege, and obviously it's similar to man in the middle attack. So okay, yeah, so let's see some stats. Currently, there are 27 billion active devices, IoT devices connected, and it's according to 2017 report, and it will gonna rise up to 125 billion. So you can see it's almost like 5 times. You can see there also consumer sector is the largest one in which IoT devices are used, and you don't want your users to like get infected. Your users IoT device to get infected with malicious updates. So here are like the firmware blues attack that I told you before. 77% increase, like DDoS 60% increased. So here, let's see. Okay, so now let's understand how OTA works over the update technology, over the air update technology. So the first one is you have your source file, C source file, in which your firmware is written. Then you compile it to object files using a compiler, and then you link it using a linker to a binary file. And then when you have a binary file, you upload this binary file to your centralized OEM server. And then the IoT device, which you can see at the bottom, that pulls the update from the centralized server, pulls the update as well as the hash, and then it recalculates the hash. We can see it this in the next slides also. So you can see here, first vendor service pushes the update binary file to the server through a HTTP request, and you get a HTTP response back. After this, the vendor service creates an MQTT call to the IoT device. So you can see here, after that, the IoT device will know that, okay, there is a new update here, and now you have to update update to the latest version. So from here, the IoT device will pull the latest binary file, as well as it will pull the hash of that binary file to validate if it is if it is not malicious. So here you can see in the instructions, you can see it recalculates the hash by hashing the binary file, and then compare it to the hash that it got from the centralized server, right? Then if it is okay, then it like updates to newer version, or it just roll back to the old version. So yeah, so there are a few challenges in this. So first one is man in the middle attack. So when you are sending both the hash as well as the binary file from the same server, you can make it different also, but the problem is any attacker can sniff in between. Like you have your Wi-Fi and you have your IoT device connected to that Wi-Fi. Then anyone can sniff in between, read that packets, make changes to that packets, or like change whole binary file, and then your IoT device will receive a different update. But it will not know that okay, this is not a real the actual update that it got from the centralized server. Uh, the second one is DDoS attack. Same in this case, flushes with random packets, and your device will go into a boot loop. Okay. And the third and last one is, which is the most severe one, is when your OEM server got compromised. So in this case, anyone can pushes like malicious update, and it will directly go to your IoT device and it will infect the IoT device, right? Okay, so the need of blockchain is the problem is with that server and the vendor organization part. So here the server is centralized, and we can improve this security using blockchain. So you can see when you push the update, the IoT device will pull it and send a diagnostic report back to the server, right? So we can replace it with the blockchain. It totally depends if you want to replace whole infrastructure, or like whole server, or like run the blockchain parallel to the server to save the hash of the binary file in the transactions of the blockchain. Okay, so this is how it looks when you replace it with the blockchain. What you can do is the binary file was stored in server, right? But and also the hash of that binary file. What you can do is you can move it to blockchain into a transaction, and then you can send instead of sending a hash of that binary file, you can send this transaction hash of the block in the blockchain. So after, like you can see when the this installation is happening, when the IoT device calculates the hash, it can query the blockchain through some intermediary HTTP server, can query the blockchain and get a Boolean value, suppose true or false, and based on that, it can either update or deny the update, right? So this is the architecture. I'll show more architecture ahead in the presentation. Okay, so for those who don't know about like what is blockchain, blockchain is basically a piece of a linked list or pieces of blocks that are connected with each other, and each block stores some transaction or some data, and each block is connected to its previous block through the through the hash of that previous block, right? Okay, so to manage this blockchain, there comes a concept of nodes. So this node is basically a Bitcoin node, your Ethereum node. So node is basically a software in which your whole networking layer, whole consensus mechanism, all these things are written, and how to manage that blockchain, all that code is written in this node. And this is actually a single node. Anyone can attack this node and change any of the block. It would be not that easy to change one block, because if you want to change one block, you have to recalculate nonce for all the blocks, which is very hard. But when you connect it to the network, now you have a network of nodes. So here if somebody tries to attack one node and maybe two nodes and change something in both of the nodes, so what happens here is consensus mechanism won't allow to do this, because you are like directly changing into the node, and the other node has already those update blocks already like attached to the whole chain. So you have to hack the whole node or whole chain in order to change the update. So this is very hard, and that's why you can replace your server, like centralized server, with whole network of whole network of nodes. Okay, so these are the benefits if you use it. First one is your immutable ledger, in which you can store your update or your transaction hash, depends on the blockchain you are using. Okay, and second thing is smart contract reinforcement. So smart contract basically is a piece of code that is deployed on blockchain. So and it is run on the blockchain only. So no one has the authority to claim that okay, this is my code and I will only run it. If it is on the chain, then whole network owns it. Okay, so you can write your logic of update, whole update procedure, whole update flow in this smart contract, and you can deploy it on the chain, and it will run automatically based on the conditions when it is when they are met. Third thing is decentralized security. Obviously, that I told before, this is a network, and you have to gain majority of the network power in order to change anything into the network. Okay, so now let's see the implementations, how you can implement this. So there are two blockchains you can use, two types of blockchain you can use. First one is your private blockchain, and second one is your public blockchain. So in private blockchain, obviously your network will be private. If you're a company, you don't want your update to get pushed into a public infrastructure, then obviously you will need a private blockchain. Second thing, obviously public blockchain like Ethereum. So Ethereum, Bitcoin is a public blockchain. If you do anything, a whole world can see it easily, right? So this Ethereum is basically public blockchain, but Ethereum has a tool called Geth. Which is basically Ethereum node. You can fork that and create your own blockchain, own private blockchain also, using a proof of authority consensus mechanism. Either you can use Ethereum or you can use Hyperledger Fabric, which is maintained by Hyperledger Foundation in collaboration with Linux Foundation. So this blockchain is for industry corporate users, and this is basically a blockchain framework. You can use this to create your own chain, launch your own infrastructure. Third one is Polkadot Substrate. So it's similar to Hyperledger Fabric, but it is much more customizable. It is created by Polkadot Foundation, and it is written in Rust. So you can easily fork it. You can add smart contracts features to it. You can change whole logic of the chain. You can do anything if you have this Polkadot Substrate framework code, right? Okay, so basically, actually I read a research paper on this. That's why I got this idea about this. So there were like 4 or 5 research paper published about this topic. I read them and I thought, okay, let's build this. They also built this and tested it. So in a hackathon, we actually built this using Avalanche Hyper SDK. It's similar to Polkadot Substrate. It's also a framework. You can use it to create your own chains, same customizability, but Avalanche is very much faster than Polkadot Substrate. So your updates will be pushed very quickly. It's like 65,000 transactions per second. As compared to Ethereum, it would be like 15 blocks in half an hour, or I guess 1 block half an hour. I'm not sure about that, but yeah. So now here you can see this is the vendor service. That is our blockchain part. And this is our IoT device, right? So what vendor do is vendor pushes an update to the Hyper VM, which is a virtual machine, basically a node in Hyperledger. In this our Avalanche subnet network. So when the update is pushed to that network, the network what it do is it pulls that binary file, right? And then it uploads it to IPFS. So IPFS basically a blockchain-based decentralized storage, right? So it stores your binary file there, and now no one can change it when it's stored in the IPFS, right? And after that, it gets the URL and map that URL into the blockchain that, okay, this is the update for this device, and this, like the parameters you passed during the HTTP request phase. And after this, all the URL and the info about the update will be stored in the blockchain. And after this, you can create an MQTT call for the IoT device. And now the IoT device will know that, okay, this is the update, new update, and I should pull it. But in this case, you will just give a transaction hash that, okay, this is the new update. You have to pull this update, right? In the previous case, you have to give whole binary file and the transaction hash. But in this case, you will just give the transaction hash, and the IoT device will just query the HTTP node exposed from the Hyper VM, one node, or it can query multiple nodes also, and then pull the binary file from the IPFS, right? and also pull the hash of that binary file from the blockchain. And now this IoT device will have both the things, and it can easily like recalculate the hash and check if it is matching and perform the update, right? Okay, so yeah, perform the update. Cool. So this is whole infrastructure. We also have like block explorer, which is basically you can see the transaction or the updates that you pushed. You can see all of that in this snow trace block explorer. So all this infrastructure, we tested it on our local host. This is for a hackathon. We won first prize in that. And okay, so yeah, so this is basically the smart contract reinforcement here. So what you can do is for verifying the hash of the like uh, hash of the binary, what you can do is you can calculate the hash, and then you get the hash, then you can query the blockchain. Okay, this is the hash what I got for this transaction ID, right? And use in that verify function. And this is whole smart contract, this is all smart contract deployed on the chain. And then the chain will, this contract will calculate, okay, if the hash matches, and then it will just send a boolean value back to our IoT device, and it will just update the system, right? Okay. Okay, so now let's see what are the resilience against these attacks that I mentioned you before. So this I took from a research paper, some of the research papers, because we actually tried it on our system and we didn't got any expected result, because we developed that in like 2 or 3 days. So, but we still managed to find some research paper and the analysis they did. So here, what they did was for denial of service, they that the OTA library, the over the update over the air update library for ESP8266 was like vulnerable for this DDoS attack. So they created a script and pushed a new update. Basically, new update means random data to the node. So it was not update; it was like random data, and they DDoSed it, and they got after some time they got this timeout update rejected error. So here because they got this because the ESP32 tried to like get that data and calculate the firmware hash, and then it queried the blockchain. And when it queried the blockchain replied, okay, this is not a valid firmware update that our company sent to this device. So that's why it got like resistance from this DDoS attack. The second one was like man in the middle attack. So obviously spoofing in between the network and then pushing the update to like the IoT device. So here in this case also it like started the verification. You can see verifying with blockchain. So it sent the calculated binary hash to the blockchain, and then the blockchain obviously replied false, and then whole verification phase like you can see failed and aborted and rebooted back to its previous firmware. Okay, so so I think we have time. So I cannot show you the actual demonstration because it's very too long. But I recorded a video in another conference, so I'll quickly show that to you. Okay, so now I'll demonstrate. Okay. We uploaded to your IPFS via the update CLI only. So if I go here, you can see this hyper OTA. This library we built using elegant OTA, which is this hyper OTA is basically fork of elegant OTA, and we have changed some code to call our chain and then get the validation of that hash, binary hash. And we will upload this into our ESP32, which is here. Currently, it is connected like wired connection, but this Wi-Fi is connected to my like home router because like we connected this wiredly because we wanted to see the serial outputs and of whether the update is happening or not. So okay, now I'll upload the initial code to my ESP32. Okay, so here I updated, like like initialize my IoT device with the new firmware, and after this, what I'll do, I'll push the firmware from the blockchain. So you can see after this. Okay, so it will really sorry for that. Wait. So now I'll this data. Okay, so here you can see the update is done, and okay, rest is here. Here you can see this. So okay, the response is our transaction ID of this data. So we can just call the chain using this transaction ID, and we'll get this data back. Now we'll create an update to this transaction ID, so that like this transaction ID is basically pointing towards our project, and our single project will have multiple updates for that. So that's why we are pointing it using our transaction ID, our device name, and our version name with the binary file. So what we'll do is we'll just change something here. We'll change. Okay, we'll change this dot to plus, which means these consecutive dots will be now displayed as plus. We will compile it again, and then what I'll do is delete this file and copy it from the build. So okay, the build is successful. We'll copy it and then we'll paste it here. So now the blockchain. First, the binary file will be uploaded to decentralized storage, which is IPFS, and then the URL of that binary file will be mapped into a chain data being happening. Okay, so here I push the binary file into the blockchain, and after this you can see I pulled the update. You can see just a HTTP call, and you can see the data is there stored into the blockchain, and then these are the like the project library a code. You can just go here or like just connect with me. I'll provide this. After this, I push the firmware for this device IP, and you can see after this. Send it. Now, if we see here, you can see the update is happening, and the vendor service to the chain to get the valid transaction. The valid hash of this firmware update. It's valid, and so you can see the consecutive dots were replaced with the plus. So the firmware is actually updated through the blockchain, right? So yeah, so this was the demonstration, and yeah, so these are the sources. You can refer to this if you these papers if you want more knowledge about this. And thank you so much. I hope you learned something awesome, and hope you learned something amazing. Thank you so much.